Hi, my name is Josephine, and I will present our work on probabilistic uncertainty quantification of prediction models with application to visual localization. In this work, we present a general uncertainty prediction framework and show an application of our approach in the context of visual localization problem. I will first briefly introduce the problem of visual localization. Suppose we have a database of images with known locations. Given a query image of unknown location, we retrieve the closest image from the database and use its location as the prediction. I will now explain our location prediction pipeline. We can first extract the features of each of the image in the database. Given a query image, we also extract its feature and perform a global feature matching with the database images. Then we can obtain top-end candidate images. We then perform key point matching to the candidate images. We define the closest image to be the image with the most number of key point matching. In many applications, besides obtaining good prediction, it is also important to obtain an accurate uncertainty quantification of the prediction. This is the focus of our paper. For a specified confidence level, for example 90%, our uncertainty prediction model will output an error bound, for example 1.2 meter. This means that the model is 90% confident that the prediction error is smaller than 1.2 meter. To do this, we leverage the concept of sensor models in estimation frameworks. For traditional sensors, manufacturers typically provide error model specifications that indicate the accuracy of the sensor under different conditions. For instance, the accuracy of a LiDAR as a function of range. We propose creating a sensor error model that maps an internal output of the prediction model, in our case number of key point matching, to the uncertainty. I will describe the process of creating sensor error model for one database. We take an image from the database as a query and use another database as the library to search from. We perform location prediction pipeline and get the closest image and the corresponding location prediction. We also have the number of key point matches between the query and closest image, and we can evaluate the distance error. We repeat these steps using every single image of the database and get a list of number of key point matches and distance errors. This can be summarized in a plot. Then we repeat the process using all databases other than the database XL itself as the library or database, and we get multiple plots. This process is actually analogous to cross-validation, and then all these plots can be combined into one plot. We can divide the data into bins according to the number of key point matches. For each bin, we can empirically determine the error bound for a confidence level, as we will illustrate later in the inference. Then we create the sensor error model for all databases and store them for inference. Next, we describe the inference process. Given a query image of unknown location, we apply the prediction pipeline. Suppose the closest image comes from database XL. Then we retrieve sensor error model from that database, and we refer to the bin associated with the number of key point matches between query and closest image to give us the corresponding error bound at any confidence level C. Specifically, we find an error value sigma C such that C fraction of the data in the bin has smaller error than it. We test our approach using the Ithaca 365 dataset where data was repeatedly recorded along a 15-kilometer route under diverse conditions. We use 9 traversals as the database or library, 3 from sunny, snowy, and night. And we use another 3 traversals as the query for testing. First, we evaluate the correctness of our uncertainty prediction on location prediction using image retrieval. For a given expected confidence level C, we can compute the observed confidence. That is the frequency that the location error is below the predicted uncertainty. We plot this expected confidence versus the observed confidence in a reliability diagram. The reliability diagram shows that our method produces accurate probabilistic confidence. This is evidenced by the small gaps between observed and expected confidence at all levels and across all 3 conditions. Next, we run a full visual localization pipeline in a driving scenario where new image measurements are received as we drive along. We run a sigma point filter using our location prediction output as the measurement value and our uncertainty prediction to construct the measurement covariance. We show a comparison to the constant covariance baseline commonly used in Kalman filter. The constant covariance value is obtained by tuning on the validation data. Both our method and the baseline receive the same measurement factors but use different measurement covariance. We show that a good uncertainty model can improve localization accuracy even with the same measurement quality. Our method also produces more accurate uncertainty estimates indicated by the covariance credibility. Most modern estimation frameworks also employ sensor measurement gating to decide whether to accept or reject a measurement. So we employ this gating technique and show the results for 1 and 2.5% levels. However, sensor gating is sensitive to the hyperparameter and sometimes results in much worse performance. The results indicates that the errors produced by the deep learning algorithm do not conform to a Gaussian error model, which is very essential to the chi-square test. Fortunately, a key novelty of our approach is that it does not require a formal outlier rejection method. In conclusion, our method can output accurate uncertainty with no additional training. While we focus on a visual localization problem, our method is general and can be applied to other problem setups. Thank you.